On behalf of the American Statistical Association, it is my pleasure to welcome you to this presentation by Professor George Box of the University of Wisconsin. This videotape is part of the American Statistical Association's ongoing program for the filming of distinguished statisticians. The objective of this series is to capture an historical perspective of those persons who have contributed so much to the development of the theory and practice of statistics. Dr. Box was born in England and did his undergraduate work in chemistry. It was while working as a chemist on laboratory experiments that he became interested in statistics and the design of experiments. His formal education in statistics culminated with a PhD degree at the University of London in 1952. He also holds a Doctor of Science degree from the University of London and an honorary Doctor of Science degree from the University of Rochester. He was head of the statistics group at the Dyestuffs Division of Imperial Chemicals Industries in England in the mid-1950s and came to the United States as the director of the Statistical Techniques Research Group at Princeton University in 1957. He moved to the University of Wisconsin in 1960 and founded the statistics department there. Few persons have had a greater impact on the use of statistics in science and engineering. Dr. Box is the principal architect of advances such as response surface methodology and evolutionary operation. He has also made many significant contributions to time series analysis, robustness, inference, and other areas. In each instance, his contributions were stimulated by practical problems. He has published more than 110 research papers and is the co-author of 6 books. The importance of his work has been recognized by major awards from the Royal Statistical Society, the American Statistical Association, the American Society for Quality Control, and the American Institute of Chemical Engineers. He is a fellow of the American Academy of Arts and Sciences, the American Statistical Association, the Royal Statistical Society, and the American Society for Quality Control. He has also served as president of the American Statistical Association and the Institute of Mathematical Statistics. Dr. Box's work has resulted in many significant contributions to the use of statistics in industry, particularly the chemical industry. His work on response surface methodology and design of experiments is standard operating procedure for many scientists working in research, new product development, process improvement, and manufacturing. His evolutionary operation technique has been used by many companies to improve process yields and reduce costs. Statisticians and other scientists and engineers are indebted to him for his extensive writings, consulting, lecturing, and short courses on industrial statistics. Dr. Box is also known worldwide for his pioneering work with the late Dr. Gwilym Jenkins on time series analysis. The Box-Jenkins approach, as it is fondly referred to, has been found useful in the modeling and control of industrial processes, economic forecasting, inventory management, and in the analysis of environmental data. Dr. Box has many other interests in addition to his professional activities. He's also known for his storytelling, songwriting, acting, poetry reading, and his interest in politics. Dr. Box's lectures are always lucid, entertaining, and stimulating. He has selected for this lecture the topic, The Importance of Practice in the Development of Statistics.
The importance of practice in guiding the development of statistics hardly needs emphasis, and yet I think it is worth examination, for statistical methods and statistical theory, like so many other things, evolve by a process of natural selection. Least squares, invented at the beginning of the 19th century, is alive and well, but the coefficient of colligation is now seldom used. For development to occur, both appropriate tools and motivation are needed. An important motivation is the practical need to solve problems. The tools are mathematics, numerical analysis, and computation. Tools and motivation interact, of course. For example, the existence of fast computers is encouraging the development of new statistical methods, which would have been quite impossible without them, and which presage further theoretical development. Again, advance must sometimes wait on knowledge of appropriate mathematics. Thus, Fisher's ability to solve the distributional problems of correlation and of the linear model rested strongly on his facility with n-dimensional geometry, which his contemporaries lacked. It would be hard to argue, however, that any one deficiency in the toolkit is disastrous. Thus, least squares, although according to Gauss, fully known to him in 1796, could require calculations which were dauntingly burdensome until the onset of modern computers in the 1950s. Again, Galton, Gossett and Wilcoxon, pioneers respectively in the concepts of correlation, studentization and non-parametric tests, did not regard themselves as particularly competent mathematicians. In particular, Gossett's derivation of the sampling distribution of what we now call the t-statistic must surely stand as the nadir of rigorous argument. But he did get the right answer, and he was first. My theme then will be to illustrate how practical need often leads to theoretical development. Early examples would be the development of the probability calculus, which was closely bound up with the desirability of winning at games of chance. The introduction of least squares by Gauss to reconcile astronomical and survey triangulation measurements, and the invention by Laplace of ratio estimators to determine the population of France at the request of Napoleon. Let us then consider some of the children of necessity produced in more modern times. In the middle of the 19th century, the impact of Charles Darwin's ideas was dramatic. But Darwin, although an intellectual giant, had little mathematical ability. To Francis Galton, the challenge was obvious. The rightness and further consequences of Darwin's ideas must be demonstrable using numbers. For example, given that offspring varied about some kind of parental mean, why, with each new branching of a family tree, did not variation of species continually increase? The answer to this practical question lay, he discerned, in the regression towards the mean implied by the bivariate normal surface, which ensures that, on the average, sons of 6 feet fathers are less than 6 feet. Again, it was the need which he perceived of a measure of the intensity of the partial similarities between pairs of relatives that led to his introducing the concept of correlation. That was an idea that was taken up with great enthusiasm and further developed by Karl Pearson. Pearson was a man of enormous energy and very wide interest, including social reform and the general improvement of the human condition. He was, however, conscious of the fact that in deciding what kind of reforms ought to be sought, good intentions, although necessary, were not always sufficient. A course of action based on the accepted belief that alcoholism in parents produce mental deficiency in children might be ill-advised if, as he demonstrated, that belief was contradicted by the data. Obviously, correlation might be useful in such studies, but other measures and tests of association were needed for qualitative variables. Pearson developed such tools, and in particular his chi-squared test for contingency tables. Karl Pearson's methods were developed mainly for large samples, and as they stood, they did not meet the practical needs of W.S. Gossett, William Seeley Gossett, when he came to study statistics for a year at University College London in 1906. Gossett had graduated from Oxford in chemistry and had gone to work for Guinnesses. Following their policy begun in 1893 of recruiting scientists as brewers, he soon found himself faced with the analysis of small sets of observations coming from the laboratory, from field trials, and from the experimental brewery of which he was placed in charge in 1905. The general problem Gossett faced was how to deal with unknown nuisance parameters, and specifically the unknown standard deviation in the comparison of means. The method then in use was to substitute some sort of estimate for an unknown nuisance parameter, and then to assume that one could treat the result as if the true value had been substituted. While this might provide an adequate approximation for large samples, it was clearly inadequate when the sample was small. Furthermore, he didn't find, nor expect to find, that there was much interest in his problems. He wrote to Fisher on the t-tables that "you are probably the only man who will ever use them." It must have been clear to him that at that time, if anyone was to do anything about small samples, it would have to be himself. Gossett's invention of the t-test was a milestone in the development of statistics because it showed how, by studentization, account might be taken of the uncertainty in an estimated nuisance parameter. It thus paved the way for an enormous expansion of the usefulness of statistics, which could now begin to provide answers for agriculture, chemistry, biology, and many other subjects where small samples rather than large samples were the rule. Fisher, as he always acknowledged, owed a great debt to Gossett, both for providing the initial clue as to how the general problem of small samples might be approached, and also for mooting the idea of statistically designed experiments. When Fisher went to Rothamsted in 1919, he was one of a member of young scientists newly recruited by Russell. He was immediately confronted with a massive set of data, rainfall every day and harvested yields every year for 13 broad bulk plots that had been fertilized in the same pattern for over 60 years. As might be expected, his analyses were not routine. He introduced distributed lag models, orthogonal polynomials, an early form of the analysis of variance, and the distribution of the multiple correlation coefficient. Also, to check the fit of his model, he considered the properties of residuals. Furthermore, he devised ingenious methods for lightening the burdensome calculations which had to be made at that time on a desk calculator. But the most important outcome of this raking over the muck heap, as he called it, and of analysing other field experiments which he had no part in planning, came from the very deficiencies which these data presented. It was the invention of experimental design. How, he was soon led to ask, might experiments be conducted so that they unequivocally answered the questions posed by the investigator? One can clearly see the ideas of randomization, replication, orthogonal arrangement, blocking, factorial designs, measurement of interactions, confounding, all developing in response to the practical necessities of field experimentation. Design and analysis came to play complementary roles in Fisher's thinking, so that over the period 1916 to 1930, we can see the analysis of variance first hinted at, and then developed and adapted to accompany the analysis of each new design. It is in 1923 that in a paper with W.A. Mackenzie, the analysis of variance first appears in the tabular form with which we are all familiar, but the object of that investigation was to solve an agricultural problem. And it's typical of Fisher that there is no reference in the title of the paper to the analysis of variance or to any of the other new statistical ideas which the paper contains. The paper's called The Manurial Response of Different Potato Varieties. In it, we are introduced not only to the analysis of variance for a replicated two-way table, but also to its partial justification by randomization theory rather than normal theory. In addition, he presents a method of analysis only recently rediscovered using models which are non-linear in the parameters. There now existed at Rothamsted a centre where careful statistical planning was going into the process of generation and analysis of data, coming from a host of important problems. Fisher left Rothamsted in 1933 and was succeeded by Yates, who had come 2 years earlier, and was not only a mathematician, but had much practical experience in least squares calculations in geodetic survey work. Yates made many important advances. In particular, he further developed factorial designs and confounding, invented many new designs, including balanced incomplete block arrangements, and showed how to cope when, as sometimes happens, things went wrong and there was missing data. These ideas found wide application and inspired much research. For example, Jack Newton, then working at the Boyce-Thompson Institute, was involved in an investigation of the infective power of crystalline preparations of the tobacco mosaic virus. Not only did the test plants vary from one to the other in their tendency to infection, but leaves from the same plant varied depending on their position, and each plant could not be relied upon to provide more than 5 experimental leaves. In response, Uden invented what came to be called the Uden square, a design which stands in the same relationship to the Latin square as the balanced incomplete block does to the randomized block design. Later, another important development coming from Rothamsted was fractional replication. Fisher had pointed out that in suitable circumstances, adequate estimates of error could be obtained in large, unreplicated factorials from estimates of high-order interactions which might be assumed negligible. In 1945, David Finney, responding to the frequent practical need to maximize the number of factors studied per experimental run, further exploited this possible redundancy by introducing fractional factorial designs. These, together with another broad class of orthogonal designs developed independently by Robin Plackett and Peter Berman in response to wartime problems, have since proved of great value in industrial experimentation. An isolated example of how such a design could be used for screening out a source of trouble in a spinning machine had been described as early as 1934 by LHC Tippett of the British Cotton Industry Research Association. The arrangement was a 125th fraction of a 5 to the 5th design. It seems that whenever a good source of problems existed in the presence of a suitably agile mind, new developments were bound to occur. Thus, the pressing problem of drug standardization in the hands of J.H. Gaddam, C.I. Bliss, and again D.J. Finney, gave rise to modern methods of bioassay, using probits, logits, and the like. While in 1940, a study of the standardization of insulin led Edgar Feiler, working for Boots Pure Drug Company, to a resolution of the problem of finding confidence limits for a ratio and for the solution of an equation whose coefficients were subject to error. Earlier, Henry Daniels, then a statistician at the Wool Industries Research Association, showed how variance component models could be used to expose those parts of a production process responsible for large variations. Variance component analysis has since proved of enormous value in the process industries and elsewhere. Well, actually, Daniels' contribution was one in a series of papers on industrial statistics read in the 1930s before what was then called the Industrial and Agricultural Research section of the Royal Statistical Society. The leading spirit in getting this section moving was Egan Pearson, whose ideas greatly influenced and were influenced by this body. In particular, he liked data analysis and graphical illustration, and used it effectively to illustrate Daniels' conclusions. An important influence on Egan Pearson was the work of Walter Shewhart on quality control. This work, and that on sampling inspection by Harold Dodge, heralded more than half a century of statistical innovation coming from the Bell Telephone Labs. This has led most recently to rekindling of interest in data analysis in a much-needed revolution led by John Tukey. Another innovation guided by practical matters was, another innovator, I should say, guided by practical matters, was Frank Wilcox, a statistician for the Lederle Labs of the American Cyanamid Company. Just after the Second World War, in the age of desk calculators, Frank found himself confronted by the need to make thousands of tests on samples from the pharmaceutical research then in progress. He said it was the need for quickness rather than anything else that led to the famous Wilcoxon tests, the precursors of much subsequent research on non-parametric methods. M.S. Bartlett's contributions to statistics are legion, but one would certainly suppose that his early contributions to the theory of transformation had much to do with the fact that when he was statistician at the Gillett's Hill Agricultural Research Station of Imperial Chemical Industries, he was much concerned with the testing of pesticides, and so with data that appeared as frequencies or proportions. Another clear example of the practice theory iteration is seen in the development of parametric time series models. In 1927, Udny Yule was trying to understand what was wrong with William Beveridge's analysis of the wheat price data. The fitting of sine waves of different frequencies by least squares had revealed significant oscillations at strange and inexplicable periods. Ewell suggested that such series ought to be represented not by a deterministic function subject to error, but by a dynamic system, represented by a linear difference equation, responding to a series of random shocks. This model was likened to a pendulum being periodically hit by peas from a pea shooter. Ewell's revolutionary idea, with important further input from Slutsky, Wald and others, was the origin of auto-regressive moving average models. Unfortunately, the practical use of these models was for some time hampered by an excessive emphasis on stationary processes which varied in equilibrium about a fixed mean. The requirement for stationarity was that the characteristic polynomial of the autoregressive part of the model had to have all its zeros outside the unit circle. Many of the series arising in business and economics did not, however, behave like realizations from such a stationary model. Consequently, for lack of anything better, operations research workers led by Holt, Winters and Brown began in the 1950s to use the exponentially weighted moving average of past data and its extensions for forecasting a series of this kind. This weighted average was introduced at first on purely empirical grounds. It seemed sensible to monotonically discount the past, and it seemed to work reasonably well. However, in 1960, Muth showed, rather unexpectedly, that this empirically derived statistic was actually an optimal forecast for a special kind of autoregressive moving average model. This model was not stationary. Its autoregressive polynomial had a root on the unit circle. The general class of models with roots on the unit circle, where stationarity would forbid them, later turned out to be extremely valuable for representing many kinds of practically occurring series, including seasonal series. The Second World War was, of course, a stimulus to all kinds of invention. Alan Wallace has described the dramatic consequence of a practical query made by a serving officer about a sampling inspection scheme. The question was of the kind: suppose from a sample of 20 items, 3 is the critical number of duds. If it should happen that the first 3 components tested are all duds, why do we need to test the remaining 17? Wallace and Milton Friedman were quick to see the apparent implication of this question, that super powerful tests were possible. However, their suggestion that Abraham Wald be invited to work on the problem was resisted for some time. It was argued that this would clearly be a waste of Wald's time, because to do better than the most powerful test was clearly impossible. What the objector had failed to see was that the test considered was most powerful only if it was assumed that n was fixed. And what the officer had seen was that n did not need to be fixed. It is well known how this led to the development of sequential tests. It is heartening that this particular happening even withstood the scientific test of repeatability, for at about the same time and with similar practical inspiration, sequential tests of a somewhat different kind were discovered independently in Great Britain by George Barnard. Nor was this the end of the story. Some years later, Ewan Page, then a student of Frank Anscombe, while considering the problem of finding more efficient quality control charts, was led to the idea of plotting the cumulative sum of the deviations from the target value. The concept was further developed by Barnard in 1959, who introduced the idea of the V-mask, a V-mask, to decide when action should be taken. The procedure is identical to a backwards running two-sided sequential test, as you see. Q-sum charts have since proved to be of great value in the textile and other industries. In addition, this graphical test has proved its worth in the post-mortem examination of data, where it can point to the dates on which critical events may have occurred. This sometimes leads to discovering the reason for the events. A pioneer of graphical techniques of a different kind is Cuthbert Daniel. an industrial consultant who has used his wide experience to make many contributions to statistics, an early user of unreplicated and fractionally replicated designs. He was concerned with the practical difficulty of estimating error. In particular, he was quick to realize that higher order interactions sometimes do occur, and when they do, it is important to isolate and study them. His introduction of graphical analysis of factorials by plotting effects and residuals on probability paper has had a major consequence. It has encouraged the development of many other graphical aids, and together with the work of John Tukey has contributed to the growing understanding that at the hypothesis generation or model modification stage of the cycle of discovery, it is the imagination that needs to be stimulated, and that this can be done by graphical methods. Well, obviously I could go on with other examples, but at this point I should like to draw some interim conclusions. I think it's possible to see important ingredients leading to statistical advance. They are the presence of an original mind that can perceive and formulate a new problem and move to its solution, and secondly, a challenging and active environment for that mind conducive to discovery. Gossett at Guinness's, Fisher and Yates and Finney at Rothamsted, Tippett at the Cotton Research Institute, Uden at the Boyce-Thompson Institute, with which organisation Wilcox and Bliss were also at one time associated, Daniels and Cox at the Wool Industries Research Association, Shewhart, Dodge, Tukey and Colin Mallows at Bell Labs, Wilcox and the American Cyanamid, Cuthbert Daniel in his consulting practice, are all examples of such fortunate conjunctions. Further examples are Don Rubin's work at the Educational Testing Service, Jerry Friedman's computer-intensive methods developed at the Linear Accelerator, George Chow's development of multiple time series for dealing with environmental and other types of data, Brad Efron's interaction with Stanford Medical School, the late William Jenkins' application of time series analysis in systems application, and John Nelder's development of statistical computing at Rothamsted. One message seems clear. A statistician who believes himself capable of genuinely original research can find fulfillment in a stimulating investigational environment. Also, I think it is possible to understand something of the specific nature of the contribution coming from applications. Frequently, it is the establishment of a new frame of reference for a problem. This may involve extension, modification, or even abandonment of a previous formulation. It has to be understood that statistical problems are frequently not like, for example, chess problems, which require white to mate in 3 moves given a particular configuration of the pieces. Here, a solution based on the pretense that a knight can move like a queen would be unacceptable. Yet, the changes in the rules that have sometimes been adopted in reformulation of statistical problems must, at the time of their introduction, have been thought of as little short of cheating. Some examples would be Fisher's replacement of the method of moments by maximum likelihood, Yates's use of designs in which the number of treatments exceeded the block size, Yule's introduction of stochastic difference equations, replacing deterministic models, Wald's and Barnard's introduction of sequential tests to replace fixed sample tests, Page's and Barnard's introduction of quality control charts, in which the cumulative sum of the deviations rather than the deviations themselves was plotted, and Finney's use of fractional rather than full factorials. Again, Fisher's use of the randomization test to justify normal theory tests as approximations is another example. Daniels and Tukey's initiation of informal graphical techniques rather than more formal procedures in data analysis, another one. I want to use the time that remains to discuss one further matter that I think is greatly clarified by the practical context of its application. This is the problem of statistical inference. Here, the consideration of scientific context provides, I believe, a resolution of what is sometimes called the Bayesian controversy. At its most extreme, this controversy is a dispute between those who think that all statistical inferences should be made using a Bayes posterior distribution, and others who believe that sampling theory, that is frequentist theory, has universal inferential applicability. I have recently argued that the Bayes sampling theory controversy arises because of an erroneous tacit assumption that there is only one kind of scientific inference for which there are two candidates, whereas I believe a study of the process of scientific investigation itself shows that it requires two quite different, quite distinct kinds of scientific inference, for each of which one and not the other of the Bayes sampling candidates is appropriate. One kind of inference, which may be called criticism, involves the contrasting of what might be expected if the model M were true with the data Y sub D that actually occurs. This is conveniently symbolized by subtraction, Y sub D minus M. The other kind of inference, which may be called estimation, involves combination of observed data Y sub D with some model M, which is tentatively assumed true. This process is conveniently symbolized by addition, Y sub D plus M. In a statistical context, analysis of residuals, tests of fit, diagnostic checks, both graphical and numerical, formal and informal, are all examples of techniques of model criticism intended to stimulate the scientist to model building and model modification, or to the generation of more relevant data should this prove desirable. These techniques must, I believe, ultimately appeal for formal justification to sampling theory. By contrast, least squares estimation, likelihood estimation, shrinkage estimation, robust estimation, ridge estimation are all solutions to problems which would, I think, be better motivated and justified by employing an appropriate model and applying Bayes' theorem. There seem to be three distinct considerations which support this dualistic view of inference. These are: first, the nature of the scientific method; second, the physiology of the brain; and third, the mathematics of Bayes' theorem. We consider them in turn. Now, first, the nature of scientific method. It has long been recognized that the process of learning is a motivated iteration between theory and practice. By practice, I mean reality in the form of data or facts. In this iteration, deduction and induction are employed in alternation, and progress is evidenced by a developing model which, by appropriate exposure to reality, continually evolves until some currently satisfactory level of understanding is reached. At any given stage, the current model helps us to appreciate not only what we know, but what else it may be important to find out. It thus motivates the collection of new data appropriately to illuminate dark but possibly interesting corners of present knowledge. We can find illustration of these matters in everyday experience or in the evolution of a plot of any good mystery novel, as well as in any reasonably honest account of the events leading to scientific discovery. Experimental science accelerates the learning process by isolating its essence. Potentially informative experiences are deliberately staged and made to occur in the presence of a trained investigator. The instrument of all learning is the brain, an incredibly complex structure, the working of which we have only recently begun to understand. One thing that is clear is the importance of the brain of models, where past experience is accumulated. At any given stage of experience, some of the models, M1, M2, etc., are well established, others less so, while still others are in the very early stages of creation. When some new fact, or body of facts, Y sub D, comes to our attention, the mind tries to associate the new experience with an established model. When, as is usual, it succeeds in doing so, this new knowledge is incorporated in the appropriate model and can set in train appropriate action. Obviously, to avoid chaos, the brain must be good at allocating data to an appropriate model and at initiating the construction of a new model if this should prove to be necessary. To conduct such business, the mind must be concerned with two kinds of inferences. The first, contrasting of new facts, y sub d, with a possible model M. This is an operation of criticism, stimulating induction and characterized by subtraction M minus y sub d. And incorporating new facts y sub d into an appropriate model. This is an operation of estimation, which is deductive and is characterized by addition, M plus y sub d. The second circumstance which I think supports the dualistic view of inference is the physiology of the brain. With two kinds of inference to consider, it seems to be of great significance that research, which under the leadership of Roger Sperry has gathered great momentum in the past 20 years, shows that the human brain behaves not as a single entity, but as two largely separate but cooperating instruments. In most people, the left half of the cerebral cortex is concerned primarily with language and logical deduction, which plays a major role in estimation, while the right half is concerned primarily with images, patterns, and inductive processes, which play a major role in criticism. The two sides of the brain are joined by millions of connections in the corpus callosum, where information exchange takes place. It is hard to escape the conclusion that the iterative, inductive, deductive process of discovery is indeed wired into us. It is well known that while the left brain plays a conscious and dominant role, one that may be quite unaware of the working of the less assertive right brain. For example, the apparently instinctive knowledge of what to do and how to do it enjoyed by an experienced tennis player comes from the right brain. It is significant that this skill may be temporarily lost if we invite the tennis player to explain how he does it, and thus to call his left brain into a dominant and interfering mode. In this context, we see the data analyst's insistence on letting the data speak to us by plots and displays as an instinctive understanding of the need to encourage and to stimulate the pattern recognition and model generating capability of the right brain. Also, it expresses his concern that we will not allow our pushy, deductive left brain to take over too quickly and so perhaps to forcibly produce unwarranted conclusions based on an inadequate model. While the accomplishment of the right brain in finding patterns in data and residuals is of enormous consequence in scientific discovery, some check is obviously needed on its pattern-seeking ability, for common experience shows that some pattern or other can be seen in almost any set of data or facts. A check that we certainly apply in our everyday life is to consider whether what has occurred is really exceptional in the context of some relevant reference set of circumstances. Similarly, in statistics, diagnostic checks and tests of fit require, at a formal level, frequentist theory significance tests for their justification. Well, finally, the third circumstance which I believe supports the dualistic view of inference concerns the mathematics of Bayes' theorem. It would seem reasonable to require that the statistical model M, by a statistical model M, we mean a complete probability statement of what is currently supposed to be known a priori about the generation of data Y, and of the uncertainty about the parameters theta given assumptions A. At some stage of an investigation, the current model M1 would therefore be defined as you see in the equation there, which can and that equation can alternatively be factored in that way. The last factor in the second expression is the predictive distribution. This is the distribution of all possible samples of Y which could occur if the model M1 were true. After the actual data Y sub d becomes available, we have that equation. And the first factor on the right now is the posterior distribution of theta, conditional on the proposition that the actually occurring data Y sub d are realization from the predictive distribution, which results from the theoretical model M1. If, and only if, we accept this proposition, all that can be said about theta must come from the posterior distribution, and the predictive density is without informational content. However, if, as is always in practice the case, the proposition may be seriously wrong, then correspondingly residual information may be contained in the predictive density, and this can not only indicate inadequacy but even point to its nature. In particular, the relevance of the model may be called into question by an unusually small value for the predictive density for the observed sample y sub d, as measured, for example, by that expression, or by an unusually small value of the predictive density of a suitably chosen checking function, as measured in that way. The diagram which I'm now showing illustrates the idea for a single parameter theta and a single observation y. The particular case illustrated is one where, after the data have become available, it would seem more appropriate to investigate further the adequacy of the model than to proceed with the estimation of theta from its posterior distribution. There are many conclusions that flow from this approach which are discussed and illustrated elsewhere. The most important in the present context is that the investigational background against which statistics is applied seems to require that when Bayes' procedure is employed, the proposition on which it is conditioned ought to be considered in the light of the data. This can be done by appropriate consideration of the predictive density associated with the data y sub d. Such an approach can, for example, justify and suggest appropriate analyses of residuals, and at a more formal level produces sampling theory significance tests. In summary then, I've tried to show how application and consideration of the scientific context in which statistics is used can initiate important advances such as least squares, ratio estimators, correlation, contingency tables, studentization, experimental design, the analysis of variance, randomization, fractional replication, variance component analysis, bioassay, quality control, sampling inspection, non-parametric tests, transformation theory, ARIMA time series models, sequential tests, cumulative sum charts, data analysis, plotting techniques, and the resolution of the Bayes frequentist controversy. Advances of this kind are frequently made because practical context reveals a novel formulation and eliminates an unnecessarily limiting framework.